Hello. I am Xiaola Tang from the University of Electronic Science and Technology of China. Very delighted to share with you our recent work, Uncertainty-Aware Unsupervised Image Deblurring with Deep Residual Prior. In this work, to solve the uncertainty in blur kernel acquisition, we propose a dataset-free deep residual prior for the kernel-induced error that is expressed by a customized untrained neural network. With the power of deep residual prior, we then propose an energy minimization framework that integrates the respective strengths of deep priors and handcrafted priors. In this framework, given the blurry image and estimated blur kernel, we can infer the clear image and residual in a zero-shot manner. Extensive experiments show that the proposed method achieves state-of-the-art deblurring methods in terms of image quality and a robustness to different types of kernel errors. Image blurring problem is often expressed by such a convolution process. Here y and x denote the blurry image and the clear image respectively, k represents the blur kernel, n represents the additive Gaussian noise, and O times is the convolution operator. Blind methods estimate both the blur kernel and image, and non-blind deblurring that is merely to estimate the image with the given kernel. Taking blind methods as an example, such an inverse problem is often unfolded with the maximum a posterior framework. With the Gaussian noise assumption, it can be equivalently expressed as such a minimization problem, in which the key is to design a suitable prior for the clear image X and blur kernel K. However, non-blind methods are disturbed since uncertainty generally exists in the kernel acquisition process. So semi-blind methods suggest handling the kernel uncertainty by introducing the prior of kernel-induced error. For instance, here we consider explicitly involving the error term in the blurring formulation, yielding a residual term that is a convolution of the kernel error and clear image. As you can see from picture D, that the residual is an image-like signal with intriguing textures. The residual is the term that we are motivated to model in this paper. Now we come to a brief introduction to the literature of semi-blind deblurring. To our knowledge, there are handcrafted prior-based methods that incorporate general domain knowledge such as sparsity and data-driven prior-based methods which leverage the strong representation ability of neural networks and rely on the abundance and diversity of training data. However, since the structure of kernel-induced error is complex, handcrafted priors are not insufficient in characterizing complex structures of the kernel-induced error. And data-driven priors are vulnerable to out-of-distribution blurs and images. Therefore, how to design a suitable prior for it remains challenging. Here is a demo of results based on different prior for the residual. G uses handcrafted prior which is relatively impotent to characterize the complex structure of residual, and Vasu uses data-driven prior which introduces artifacts around the sharp edges. As a comparison, the proposed deep residual prior-based method delivers the most pleasing results in terms of the quality of the estimated residual and restored image. So now let's see the proposed model. We suggest the dataset-free deep residual prior represented by a customized untrained neural network that allows us to flexibly characterize the complex intrinsic structures of residuals. On the other hand, you can see that the residual is generally sparse in the spatial domain. So we utilize the sparse prior as domain knowledge to guide DRP. Similarly, we use DIP guided by total variation prior for the clear image. Here is the minimization framework. To suppress the artifacts, we also involve the ringing artifacts term explicitly in the formulation and use a sparse prior in the DCT domain. To tackle the formulated model, we suggest an alternating minimization algorithm by dividing the minimization into two easier subproblems. We use the Atom algorithm for the theta-zeta subproblem, and proximal gradient descent for the V subproblem. This is the overall alternating minimization algorithm. Given the estimated kernel and the blurry image, we can infer the clear image, residual, and artifacts. Now let's look at some experiment results. The first is the ablation study. We explore the influence of different network architectures for DRP. The results here show that the customized UNet is more capable to capture the residual as compared to FCN and UNet. And a better estimation of the residual boosts the quality of image restoration. Then we explore the influence of different combinations of deep priors and handcrafted priors. We can observe from the table that all priors are indispensable and they work together to deliver a promising result. On the benchmark dataset, the proposed method achieves state-of-the-art deblurring performance in terms of numerical and visual results. Here are the estimated residuals by different semi-blind deblurring methods. You can see our results are closest to the true residuals. And here are the results of the simulated images. Here are the results of real images. We can see that our method faithfully restores high-quality clear images and robustly handles the artifacts as compared to other methods. We also compare their robustness to different types of kernel errors. By varying the parameters of the blur kernel, we obtain a series of inaccurate kernels. Here are the results, in which the first two columns are motion blurs, and the last two are Gaussian and disk blurs, respectively. From this figure, we can see that the proposed method delivers pleasant robustness to kernel error and achieves the best quantitative performance in comparison with other methods. To summarize, we proposed an unsupervised semi-blind deblurring method that is driven by the tailored DRP. It serves as a paradigm that combines untrained neural networks with domain knowledge. Particularly, it shows favorable robustness to the kernel error. That's all, thanks for watching.